Hi, my name is Nathan Zhao, and my presentation is on understanding contrail parameterizations in the global climate model. First, I would like to thank Samuel and Berta Spalter for providing me generous funding to do my research, and then I would like to thank Ms. Carol Casey, Dr. Yuk Young, and Dr. Yuen Wang. When my surf was canceled in March, Ms. Carol provided me some excellent opportunities so that I can still do a surf this summer. Dr. Yuk Young kindly invited me to join his research team, um, and I was able to see many interesting research projects that he's been working on. And Dr. Yuen Wang has been providing me great guidance throughout this entire surf project. So I'd like to thank all three of them. So this is my project, and on the right you can see this is pretty much what a contrail is. It's synonymous with aircraft emissions, and they're composed of water vapor, aerosols, trace amounts of nitrous oxides, volatile organic compounds, and some carbon dioxide. So a key concept for my presentation is radiative forcing. It's defined as the net change in radiative flux at the top of the atmosphere, and radiative flux is just the amount of power radiated through a given area. It's pretty similar to electric flux and magnetic flux. And notice a key term I highlighted is change. So radiative forcing is basically the change in radiative flux since the pre-industrial era, which is the mid-1700s, when there were no human-caused emissions in the atmosphere. So the radiative forcing in 2020 is how the flux has changed since the pre-industrial era up to 2020. Now, models have to be used to calculate RF because there's a lack of observational data from the pre-industrial era to now. And also models are also, used to calculate RF in the future as well, and obviously there's no data in the future. So assumptions on temperature and atmospheric conditions are inputted into the models to give reliable values to calculate RF. So the atmosphere traps long-wave radiation, shown in this chart, from escaping the atmosphere, and that warms the planet. And it also reflects shortwave radiation back into space, which cools the planet. So net RF is the difference between long wave and short wave. And when this value is positive, there's a net warming of the globe. Now here's a chart relating emissions to impacts. So aircraft emissions change the atmospheric compositions, concentrations, and whenever there are more particles in the atmosphere, those particles will have an effect on like the absorption, scattering, and reflection of radiation or light. So that causes radiative forcing to change. And radiative forcing is directly related to climate change, and climate change has its impacts. Now, models for radiative forcing. Current models are crude because contrails are not uniform in the atmosphere. They vary day by day, and they only exist in areas when there's dense flight traffic. And in addition to that, there are many models which have different parameterizations, different methods for calculating RF. So all these combined will yield a range of possible RF values from contrails with low confidence because of these reasons. We can contrast this with well-mixed greenhouse gases, such as CO2, because they're pretty uniform in the atmosphere. So scientists can narrow down the concentrated values of CO2 in the atmosphere to provide a more reliable, higher confidence estimate of the radiative forcing from carbon dioxide. Now, it's interesting because in this chart, contrails seem very insignificant at this moment, but air traffic is projected to increase dramatically in the upcoming decades and will have a greater impact on the climate because there's going to be more aircraft emissions in the atmosphere. So it's good to create an effective model now so that we can model the past and the future. So like I said previously, these models are very important, and my job is to study these previous models and understand how they parameterize contrails and to get a better idea of the range in the radiative forcing values. So the research group I'm currently working in is also developing a more up-to-date model, and I'll be comparing this new model with previous models and studying the ways in which the new model is an improvement. The first model is the NASA-Langley model that uses an RTM with Contrail cloud parameterizations. So a radiative transfer model is the method to compute radiative forcing. Each unique chemical species interact with light in their own way. They have a unique way in how they respond to scattering, reflecting, absorbing light. So that adds a completely new variable in the RF calculation. The RF also varies at different heights because the absorption of infrared light changes with elevation. So there's no mathematical calculus-y way to do this. You have to input it into this model. So it basically, this model configures a chemical composition at the different heights of the atmosphere in which RF can take place. And it just measures how photons travel vertically through this vertical column. And satellites provide input data for this model, and that's why it's very crude, because satellite imagery does not provide all the observational data necessary to rigorously compute this model. We only get information on how much cloud cover there is, how thick the cloud is, and how reflective it is. What it's lacking is how each unique chemical species in the cloud responds to light and radiation by itself. All we have is how the cloud responds to it as a whole, which is not rigorous enough, and it might not provide an accurate estimation today. The next model is the Texas A&M model. It runs a full GCM global climate model along with a RTM to simulate RF from contrails. So a GCM shown on the right is a three-dimensional model with a certain horizontal resolution representing the region of interest and a number of vertical layers representing the atmosphere and the ocean. We're going to ignore the ocean because that's not relevant to this project. And it can input parameters in the GCM, and basically what it does is it simulates a climate response that gives input data to the RTM to calculate RF. For example, if I increase the amount of greenhouse gases in the atmosphere, then the atmosphere is going to respond by becoming more hazy or foggy or cloudy. More advanced optical properties were factored into the parameterization. All these optical properties are function of the particle effective diameter, which makes sense because if the particles in the clouds are bigger, they would interact with light in a different way. So the sensitivity of RF to these parameters are also studied by running the model many times while varying these parameters and seeing how the RF value responds. So essentially, to conclude this model, it inputs more advanced parameters into a GCM, parameters about scattering, absorption, polarizing properties of contrail clouds. The GCM simulates a climate system response, which gives the input data such as distribution of clouds and other chemical species from contrails into the radiative transfer model to calculate forcing. Okay, so the model that my research group is developing now is called the MCAR model. It runs a full GCM with the most advanced contrail parameterizations coupled with an RTM. So this GCM actually intakes raw data from a data set we got that is made just to be inputted into a GCM. This data set must be interpolated so that the emissions will fit the GCM resolution. It must be interpolated so that the data can fit in this 3D model without getting distorted or exaggerated in any way. We do this to conserve emission mass because we want our data set to be properly displayed in our model. And this interpolation is very complex, lots of math. Oops, sorry. So once interpolated, the GCM checks to see if the ambient conditions pass this criteria. This Schmidt-Appelman criteria is basically just saying if the ambient temperature is lower than some critical temperature and the ambient relative humidity with respect to ice is higher than this critical relative humidity, then the contrail is deemed persistent, meaning that it will last in the atmosphere for an extended period of time. So these persistent contrails will then go to increase the number of in-cloud particles and the cloud fraction in the GCM. The amount of increase of both variables is quantified by complex microphysical formulas. So these are the formulas for critical temperature and critical relative humidity. They're all dependent on constants, or critical temperature is. These constants are supplied by the GCM and the dataset. And then the critical RH is just dependent on temperature. So to the GCM model, assuming these threshold conditions are exceeded, this model now has the information on the number of particles, cloud fraction, size of particles at every horizontal range and vertical layer in the model. This information is inputted into the RTM to calculate RF in everywhere in the globe to get like a net global RF value. So in summary, this model predicts the contrail by knowing aircraft emissions and the ambient conditions, of course. When water vapor and aerosols are inputted into the atmosphere from the aircrafts, model physics calculations will yield the extent of formation of contrail clouds as long as those threshold conditions are exceeded. So those values and the chemical species profiles and vertical distribution of clouds are incorporated into the RTM to calculate RF. So this is what the model yielded. You can see the long wave contrail forcing values everywhere around the globe as long as the short wave. So this is 0.16, negative 0.19, so it yields a net global RF value of negative 0.03 watts per meter squared. And that's equal to negative 30 milliwatts per meter squared. So as you can see, it actually produces a net global cooling effect, which is different from all the previous models. So therefore, we should obviously run this model more to get a more reliable value if this was just an aberration. Better aircraft emissions data can be implemented. Our data set was from 2006 and lacks sufficient flight data in the Asian region, such as China, Thailand, places like that. We want to see why there's a strong cooling effect in the Philippines and Indonesia area in Indian Ocean. And also, a better way to look at the radiative forcing value is to study the regional RF values in areas with higher flight traffic, such as in the US and Europe, and to see how the climate responds to the heightened air traffic areas in these regions. And lastly, when we perfect this model, we want to see how net RF from contrails has changed since the COVID-19 pandemic began, because once this pandemic started, the air traffic volume was reduced significantly, and we want to ultimately see how the climate responds to that. So here are my references, and thank you for listening to my presentation.